Hello, am I audible?
Yes, so they.
Yeah, so last night we actually got two proposals that we thought we can do for the SMT project. Can we just fix the time when we can
Yes, I got your email. So let me, I will do. So I've got several proposals. I mean, I think most of the people have submitted the proposals. So I have to schedule discussion on all of them. I mean, on all of them. So I'll have to draw up a schedule. Okay. So
Yeah,
give me till the end of the day. I mean, do you when do you want to meet? I mean, we can meet immediately after the class tomorrow. Do you want to do it even earlier than that?
yeah, sure. I mean, anytime that will be
Yeah.
available.
So since you asked for the first thing, so I'm yeah. Let's do tomorrow. So I might even do, since there are quite a few proposals, do the entire class devote on that. Okay. I'm wondering. Okay. Um,
Hmm.
so yes, and if people want to discuss. So tentatively, let's agree on immediately after the class tomorrow. Okay.
Sure, yeah.
Hmm. Oh, I want to discuss. I hope I should have sent an email, I guess. 'Cause I want to make some decisions about the work uh, for the rest of the term. So I wanted the buy-in from all of you as to what I was planning. So let's wait for a few more minutes. I want to get as many people in. Huh? Okay, let's zoom into here. It's too bad. Okay. Okay, maybe I'll have to start. I was hoping Zubin would be here. Okay, first off, so you guys are all there? Can you hear me, correct?
Yeah.
Yeah. Okay, I want to discuss what I'm planning for the rest of the thing. And you still have not got the first assignment solution. So here's what I was planning. Okay. So as I said, there will be another SAT-based model checking, programming assignment, which is slightly bigger, but I'm okay if you team up, do it in pairs. Okay. Now that most likely I want to give it out on go out on third, and then you will submit it by the end of the month. Okay. And I want to have two small quizzes, one on 2 weeks from now, this week. Okay. Probably on the 12th, and the other one on the last week on two portions. I will give you exactly what the portions are. These will be small quizzes on things like testing you on CTL, LTL, some of the theoretical concepts. And I will give you the portions. I will even give you some exercises that if you kind of do, that will help you. It's up to you whether you want to work on them or use them as preparation. So that's what I'm planning. Now the weightage, I will work out, and then I will tell you exactly how I plan to distribute this this thing. Okay. So I wanted your feedback on that. Be like 2 1-hour quizzes. Okay. I'll give it to you, and either I don't know. I mean, I can give take-home quizzes, or I mean, some of the people who are doing quizzes here, I don't know about the other thing, and I suggested they have just give it, and then you just submit it. There's no proctoring or anything. I mean, I'll give the questions, and all you have to do is to submit it within 2 hours or something like that. Okay, you will have 2 hours, and that's the kind of thing that I'm planning. I mean, of course, I can give it and then have it take home for a day, but I think just a 2 hour thing is what I was planning. Okay, um, and then there will be no more assignments, but rather there will be like a programming project where you will be implementing one of the algorithms for inductive model checking that I will be covering in class. Okay. And I had already given you a heads up about doing it in pairs, and you can pick your teammates and let me know. And I want to.
Sir, what exactly do we have to submit for programming this programming assignment?
think something's well, it's a working program with outputs. You know, we'll give you the test. Zubin is here.
ಏ ಮಾ ಉದಾಟ್ಟಾಗೆಲ್ಲ ಅದು
Yeah, I mean, we will. Yeah, I can specify the deliverables, but I think it's you want the program, you know, with runs and on the test examples that we give you. I think that's the same thing that Zubin, you're here, okay? So I just want to tell you what I just now told the rest of the class, okay? I was telling them what what the work will be for the remaining thing, okay? So I said
So
that,
what have we decided about counter example generation part? Sir, actually, the algorithm that you described, I couldn't understand it properly, and I could not find any references also.
which one?
Counter example generation. Is it in the book?
It is in the book.
Okay, I'll see.
I mean, I can describe. It's good that you have brought it up. I can go through that in the next, class. I'm not. Yeah, I mean, I told you. I mean, if you have to have specific questions, since I've covered in the class and it is in the book. Okay, I can show you where it is. I think it is in chapter. It's in chapter 8. 8.5. And of course,
What have you decided about it? Will you have to implement it? I have actually done only the normal model checking part without fairness. And if counter example is also there, I'll have to further modify my code, I think.
Correct. Okay. Yeah, I think I want you to do that because there are no more assignments. Okay. And since that's the thing, so yes, I would like that to be, yes, for the normal case. Yeah. And do it for, I can, at least for one of the, yes, I mean, my simple answer to your question is I think it needs to be implemented. But if you guys are finding it very hard, then you're like, is there anybody else? How are you guys completely confused about how you want to implement? Have you even started it? Have you looked at it? And what do the rest of the people feel? The entire class feels okay. It's hard. I can't do it, and of course I can't. I'll have to relent. Okay.
I haven't tried yet, so I'll
Who is
try
this?
within
Please
this week.
introduce yourself.
Oh, I'm Shomadev. So I didn't try that counter example part, so I'm not sure.
Okay. Yeah. So what I will do is, I don't know. So I guess the deadline is long past, right? I don't know what deadline I even gave.
Uh,
Yeah.
it was 3 November something. I just saw now.
Yeah. What is the deadline?
3 November.
Or 3rd November. There's still time. Okay. So what I will do is let me discuss it in next class. Okay. I will spend part of the time in talking about that. And I will also have Zubin implemented. So, we can give some tips. And so, I'll assume that we will implement it, okay? With some assistance from us, okay? Yeah. So Zubin, what I was discussing was there will be two, like 2 hour quizzes, one on November 13th. Sorry, yeah, 2 weeks from now, which is, no, the week of November 6th. The other one on the end, okay, like 26th or so. That is the last week of classes, isn't it? 26th, or that is the exam week. Huh? 22nd through the thing on the last day. Okay. And there'll be one more programming assignment using, implementing the model checker using SAT solver. So that'll go out on November 2nd. Okay. So that's what I plan to do. Yeah. And the second programming assignment can be done in pairs. So you can pick a teammate and then you can do it together. And I will publish the relative weights of all the workload that you have for the term. Okay? I mean, for the various assignments, projects, and quizzes. Okay. That I will do. So that's what I announced. So any more questions? Okay. Yeah, so I'll be talking about inductive model checking today. And what you will be implementing is something similar to what I'll be discussing today, but a little bit more advanced variant of this technique. Okay? Okay, so just to set the context, so you saw bounded model checking, correct? So which was the idea there was to unroll the transition relation, incrementally, for, more number of times, and then check the absence of or presence of bounded counterexamples. Okay, and we saw that how that worked for mainly safety and simple liveness properties. And since that was, by definition, an incomplete method, we saw one way of completing it by coming up with approximate bounds to the how many times you need to unroll the transition relation. Okay, a bound on the longest counter examples. Okay, and we saw a couple of metrics for that. The most, and we observed that they are dependent on the property and the transition system. And for safety property and the simple liveness property, we saw that the reoccurrence diameter is a bound, okay, is a bound. And that could be computed for a given transition system by posing it, by solving an instance of a quantified SAT formula. Okay, that is one way of doing it. Now, inductive model checking is another way of completing. That is one way to view bounded model checking. All these, the reason, the motivation for bounded model checking itself was not to do this model checking without actually having to explicitly eliminate the quantifier, okay, in the image computation. Okay, so that is the idea, because that will result in an explosion of the size of the formula, especially when you will have to express it in CNF form and not use BDDs. And so that is not. So that is the that was the idea. Now, yeah. So before I get to this, I need to introduce. Yeah, it's just a recap of what invariance and safety properties are. The inductive model checking algorithms that we'll be discussing in the next few classes are all applicable to mainly invariance and safety properties. Okay? And so that's the version that we will be looking at. They are not directly applicable to liveness properties. So a Kripke model, given a Kripke model and a property, and a predicate over the state. Suppose the property P is expressed as a simple predicate over the state of the model. P is said to be an invariant property if it is true for every state that is reachable from any of the initial states. Okay, so there are properties of the kind AG of P, if you were to be expressing in CTL, or OG of P. Oh, I forgot to record. Well, that's okay. That's okay, I guess. That's okay, since it is being recorded. Fine. Now, safety property versus invariance. Actually, invariance.
Sir, the
Yeah.
slides aren't visible.
Oh, slides are not visible. Okay, I screwed it up, didn't I? But I wanted to start recording. Sorry about that. Okay. So recall how we defined a safety property. A safety property is one whose violation can be checked by witnessing a finite history. So finite path. And the counterexample is necessarily a finite path. An invariant is a special form of safety property. Okay, so where the P here has to be a simple state, a predicate. Okay. There are more general safety properties, like, for example, these kinds of things, or you can even use the until operator there, until certain things. But all those general safety properties can always be converted into an invariant property in invariant form. So where P is predicate by extending TS, by adding extra states to remember some history. So you could do that. Now, for example, AG of X of P, X of Q, it says that, okay, PQ has to appear one after the other in the history. You can imagine that this is not exactly invariant property the way I have defined it syntactically, because it has to be a predicate on a state, whereas here it is another temporal operator. but you can imagine that you can remember certain, add certain more bits or more information to the state to remember the history. And since checking a safety violation to a safety property requires you to remember only finite amount of history, you can always do that. So for this reason, inductive model checking, we will look at them only how it can be used to check invariant properties. Okay, so there is this general theorem. Liveness checking can always be reduced to a form of safety checking. Therefore, you'll see, that there is a way. I mean, we will see towards the end of this semester how this can be done when we will be introducing LTL model checking, and LTL model checking pretty much answers this this question. It will be a bigger and bigger formula. So I'm stating this theorem here because inductive model checking being applicable only to safety properties, not theoretically at least a restriction, because liveness checking can always be reduced to some form of safety checking under certain conditions. Okay, so at least when we discuss in inductive model checking, we will be restricting ourselves to checking invariant properties. So no question. I mean, I hope this is clear, correct? So invariance versus what the safety properties and what an invariant property is. Okay. So now I'm going to introduce a notion of a property being inductive, because that's what we are going to exploit in in kind of completing this bounded model checking without actually computing an actual bound on the length of the counter examples. A property P, when I say property now, assume it's an invariant property, a property of the form that I used to define invariant property. So property P, which means it's a predicate, okay? It's a predicate. P is inductive. A property means a predicate is what I'm assuming here. P is inductive for a transition relation with respect to translation if the following conditions hold. So for every pair of states, if you start with this state in which P holds, then and then you do one step of T, then P has to hold good, for all its successors. Okay. So an inductive property, informally, what inductive P is true if of every state reachable from any arbitrary state in the Kripke model, because this is kind of inductive, right? So the definition itself is inductive. So for P, that is, it's pretty much saying P is kind of closed under the transition relation T. Okay, is the definition clear? Yes. So here, if you start from an arbitrary state, C of T. So there's no mention of any initial state here, remember, okay? Because all the model checking algorithms that we were talking about right now were accumulating states from the initial states, because that's what invariants are defined. So an inductive property doesn't have to be an invariant, okay? If it is, then it is called an inductive invariant. So an inductive a property, and if a property is inductive, then checking that it is also an invariant for a crypt key model for a transition system can be done very easily. Okay, so you need to just check these two conditions, that P is inductive and that your initial set of states are included in P. See, if P is inductive, then every state in P, its successor is in it, and therefore, the entire transitive closure of states under P and under T that satisfy P will be inside P itself. Therefore, if the initial state set of states is already included in P, then any state that starts from one of the initial states and is reachable in 0 or more steps is also included in P, and therefore it satisfies P and it's an invariant. And you can see that these two checks are very simple SAT checks. Right? We want to show that these two things are valid. How do you show something is valid using a SAT solver? You will take the negation of it and then check that it is unsat. And you see, there is no unrolling for an arbitrary long unrolling off the transition relation, or even computing the fixed points, okay, for that is if you know that if it is P is inductive. So what if P is not inductive? If it is P is inductive, that's what you're checking here. Okay, but many properties may not be inductive, and that's why there is need for doing model checking and other things, because what you care about there is that things that are reachable from the initial state preserve the property P. Then, if P is not, the simple thing, only is usable only if you luck out and P happens to be inductive. So if you're able to prove it, then you know that the thing you don't need to do multiple steps of unrolling or compute the costly thing of computing the fixed point. But what do you do if P is not inductive? Then the thing is, find an inductive something else, an inductive invariant P star that is stronger than P. That is, P star implies P. So find some other predicate which implies P, which is an inductive invariant. Okay. Of course, this is not easy. This is in general an undecidable problem, and it is a hard problem. But it gives you an alternative way of proving those properties. And this concept is what is exploited in inductive model checking. Even if you're not explicitly able to find an inductive invariant, if you can perform a sufficient check using by repeated calls to a SAT solver, which guarantee the existence of an inductive invariant, then you're able to prove P. Of course, the hope is that this search for this inductive invariant requires much fewer SAT calls than your bounded model checking approach requires, going all the way to the completeness threshold. Okay, and that is the crux of the issue. So most inductive model checking methods, they try to in some cases they win over the bounded model checking approach with completeness threshold because they tend to converge much faster than the bounded model checking with completeness threshold. Okay. So any questions here? This is the general idea behind inductive model checking. Let's see an example. Okay. By the way, this is also the topic of chapter 9. Okay. No. Sorry, not 9. Chapter 10. Okay. Specifically, what I'm going to be talking today is 10.2, a method called K-induction. Okay. So let's see this simple transition system. Is the predicate P, the label predicate, is P inductive here for this transition system? Is it an invariant? Before you answer whether this P is inductive, is it an invariant?
Yes, right.
Yeah, why so?
Because it holds on all reachable states.
Yeah, so the reachable states here are from initial state is 1, 2, and 3. Okay, 4 and 5 are not reachable. So P holds good, therefore P is invariant. Is P inductive?
Yes, right. Because like whenever P holds, it holds in the all the next states.
Correct. Yeah. Now, this is very important for you to understand. So I asked this thing. So if you, if anybody has doubt about the answer to both of these questions is yes. So, if you do not understand why P is inductive, please ask me. So do you understand? Because what inductiveness check says, from an arbitrary state in which P holds, not necessarily the initial state alone. So if you put any state that in which P holds, if its successor also is also happens to be a P state, then it is inductive. Okay? So since all these, the states in which P holds are 1, 2, and 3, okay, and therefore, and each of its successor also happens to be a P state, okay. That's why P is inductive. So if you check, if you're too lazy, don't want to spend the resources to do model check, first check if the property, when you want to check if something is invariant for a transition system, check if P is inductive. If it happens to be inductive, which is a simple check, then you need to only check if the initial state is included, okay, in P. Is Q inductive? Is it an invariant? Somebody else answer?
Both yes, right? No. Q is not inductive, but it is invariant.
You're right. Okay. No for the first one, yes for the second. Okay. So the interesting thing that inductive model checking is, what do you do when the predicate that you want to show is an invariant for the transition system is not inductive? Okay, of course, you can use bounded model checking up to completeness threshold if you complete, but how do you do it? Another question. Oh, I've already given you the answer. Fine. What is the strongest inductive invariant for a model? So people understand this strength of a predicate. Okay. So a predicate P is said to be stronger than Q if P implies Q. Okay? The set, yeah. So the strongest inductive invariant for a model and is the reachable, all reachable states, the set of all reachable states from I, okay, which is a fixed point, okay? And that is, a fixed point is always inductive in, with respect to the transition relation, okay? So, and specifically, this set of all reachable states from I is the strongest one, okay? So that you can have. So model checking is also can be considered as an inductive method, but it does it by computing in some sense the strongest thing, okay, the smallest set that satisfies these. I mean, yes, okay, the strongest inductive invariant. So then, see, if you compute the strongest invariant, then you can apply it to any other, invariant property, but just checking if that property is preserved by every state in that reachable state. And that's why we'll have to do. So inductive approaches, they try to be a bit more clever. They look at the property and then try to see, can I find just a weaker than some inductive invariants that are weaker than the strongest reachable state, and yet that is strong enough to imply the property, with the hope that maybe you can converge to finding that weaker inductive invariant more efficiently. Okay, so that is the idea. So here is a pictorial view of what model checking with inductive invariants mean. Q is the set of all states. P is the property, the one, the red. So as I said, we are only looking at invariance. Invariance is characterized by a predicate on state, and that's what P is. Okay? You want to prove that the transition system whose initial set of states is I, and this arrow here represents T, is for that P is is an invariant. Okay? Now, what model checking does is it computes this reachable set of states, up to fixed point, and then checks if it is inside P. I mean, you can also do it backwards, start from P, and then you compute all the states that invariantly going to P, and then check if I is inside that. Okay, so, but anyway, it computes, forward model checking methods. They use this blue way of doing it. Inductive model checking tries to find this green thing, which is inductive, implies P, and contains I. Okay, so that's what this thing does. Okay. Okay, so you can kind of generalize this. So, like I said, P is inductive, we have the definition. We can generalize this, this inductive definition to something called K inductive. Definition, K inductive for some K greater than or equal to 1 is defined as follows. P is 1 inductive if P is inductive, as per the definition that you saw earlier. P is K inductive for some greater than 1 if you, for every path, okay, so starting from any state that satisfies P, if you consider a path in which P holds after every in every state on that chain, on that path, for up to k, states, and for up to k minus 1, 0 to k minus 1. And then if they all are, are P states, and they are a path from some S naught. See, S naught here is not the an initial state. So it is some state that satisfies P, okay? That if you can prove that the next state, the Sk that you go, the k plus 1 state, that is reachable from S naught, is contained in P, then it is said to be K inductive. Okay? Yeah. So two things. You can observe that by definition itself, P is K. If P is K inductive for some K, then it is K plus 1 inductive for all K greater than or equal to 1. So that is easy to see. Once this you are, at some step, K becomes inductive aspect, it becomes K inductive. Then after that, every state is inside P anyway. Therefore, yeah, so that is the first observation by this lemma. And what is used in this method K induction is this theorem, okay? So if P is K inductive, then there always exists a P star such that P star is one inductive, that is inductive, and P star was to be. So instead of checking, yeah, so even if P property is not inductive, then you can check if it is K inductive, okay, by doing this, this check. Of course, this is very similar to the BMC, bounded model checking formula that you use to check, but it is doing from a more general, from the property. It's kind of property directed. Okay, so we use this theorem, and the next the picture in the next slide will tell you why this is. What you need to do is, if it is not one inductive, you check if it's 2 inductive, 3 inductive, and so on. And if you come to a point where it is K inductive, by this theorem, then you know that there is an inductive invariant that is strong enough to prove the property, and it is yes. Okay, so. Yeah, so if this check holds for some K, then at that point, all you need to do is the initial state is contained in P. That's what you will have to check in order to show the thing. Is it? Yeah. So is the definition for K inductiveness clear? Okay. So let's look at this example. Again, the example that we saw. This you already answered. So the new question is, so P is already inductive, therefore it is one inductive. Is Q K inductive for some K? Q is not inductive, so obviously it's not one inductive. So is it two inductive? The Q is not inductive. Why?
Yes, it's too inductive. It's too inductive.
Yeah, so that is the thing. So it is inductive for K is equal to 2. Therefore, you see, so that check gives you faster convergence here. So if you were to do bounded model checking or general model checking, so starting from the initial state, you had to iterate for 3 times, whereas here it is enough. You get convergence from in 2 steps. Okay, and of course that includes some state that are not reachable in it. Okay, so that inductive invariant, it includes this cube, but that's okay. Okay, so as long as it satisfies the property, it is contained in the property that you want to check, and if um, the initial state is contained in that. Okay. So that is the key idea. Is it clear? So that's what, so maybe in some cases, this checking for K-inductiveness can give you faster convergence. So what is happening here? So this kind of picture shows you why, if it is K-inductive, you can always, there's guarantee that there is an inductive invariant. So what's happening here is P is not, when P is not inductive, what does it mean? It is not one inductive, say you start with. That means that there are some states, like I've shown here, these red states, that some states where one of its successor states take you out of P, like it happens here. So that's why this is not one inductive, okay? Now, so check for two inductiveness, it restricts yourself, it kind of eliminates. It says that the first state has to satisfy P, and then if all the successor states also satisfy P, if you include only those you remove those states that in one step get you out of P, that's what the induction hypothesis here really means. So then is it inductive? Okay, when I remove all the states that take you out of it in one step, suppose I remove that, and then that state, then I ask the question if it is, inductive. So it's really, that's what that inductiveness, K-inductiveness check is doing. And you repeatedly do this. In each step, you sometimes I call this thing as counter example to induction. Okay, they call it a CTI, counter example to induction. Okay, because it has a state which gets you out of it. Okay, in one step, sometimes in two steps, and so on. So each time you're strengthening the induction hypothesis in the check for K-induction here, okay, this check when you do, what you're doing is really removing states that move. There is a small mistake here, okay? So I've shown here this particular state where I'm showing the cursor also it gets you out of that state. There is a transition that gets you out of P in one step, okay? So that would not be here. That would have been removed from here in the first step itself. So that is wrong, okay? So these states that you see here are, okay, for example, the one that I'm pointing my cursor to here, that's a state which is in P but does not have any successor that gets it out of P in one step. That's why it requires two steps to remove. So and then when K, for some K that in K inductiveness check formula gets valid, then what you effectively have is, through this elimination of these things, I can always construct, if I wish to, okay, a P, a green P, a green P, which is inductive. So after that, I don't have any state inside the green ellipse that takes you out of P. Therefore, that is inductive. Okay, that's a fixed point. Okay, so you can do this, and that's one. So if indeed this is exactly the point at which the K-inductiveness check in this case too will No, not exactly 2, because there is something which has length 3 and 4 and so on. Okay, will happen. So that is the idea. So of course, in order to get that invariant, at least the way that I've shown is that you need to do existential elimination. Okay, because you will have to. If you, I mean, I have a slide where I show you exactly what the invariant is. I mean, a stupid way of, I mean, stupid in the sense an expensive way of getting this particular invariant is to eliminate we are doing, because that defeats the purpose, correct? So what I'm doing is I'm actually checking this more general condition in which starts from an arbitrary p, in which the antecedent is strengthened more and more, okay, incrementally more and more. And that's what is happening. And that's why here by, when you get check for 2 inductiveness, you have, if that is true, then you can conclude that it is inductive, and then check if I is in it, and then you're done, okay? So that is the thing. So what I'm doing here is, this is what doing in K-induction. I first check if it is what inductive. No, in this case, because there are other states there, then I do another 2 inductiveness check and so on. And at some point, you will get to something which is it is inductive. Okay, so some k, and then you can conclude. Now you can, yeah. So if the property is indeed an invariant, that's the completeness theorem. I will pose the completeness theorem later on, that which states that if a property is indeed an invariant, there always is a k. Okay, for which it is k inductive, and I'll get to the completeness part. But so with that thing, so you can always do this, and you can be sure of termination, provided it is an invariant. I mean, if it is indeed an invariant. Otherwise, there will not be. I mean, you will not be able to find for a such a k inductive check will continue to fail. Therefore, it would be useful for you to combine this with a check for presence of k-long counter example starting from the initial state, like you did in the bounded model checking. With this can be considered as a completeness check, okay? To make your bounded model checking, which was checking if there exists longer and longer counter examples of longer and longer length from I. So where there you were only doing that until you reached a completeness threshold which had to be computed independently. So instead, you can combine these two, the completeness check and the check for counterexample from initial states. Okay? So what is shown in red is the bounded model checking check. Okay, I call it the base K, but it really is checking if there are. It's exactly doing what we were doing in bounded model checking. Okay. So for each of those steps, then I also do the inductiveness check, okay? The K inductiveness check. So simultaneously, but that is done not from starting from IS1, but rather the inductiveness check is the K inductiveness check. So if I start from some arbitrary state in which P holds good, if if I assume that K, a path, a chain, a path on which P continuously a path of length K, in which every state P holds. From that, if I K plus 1 state is, you know, happens. Yeah, yeah, p holes. Okay, this is exactly the k inductiveness check. So I do this. That's what I do here. So if the initial state itself, one of the initial states itself, p does not hold, then you return a counterexample. Otherwise, you keep doing the following two things. You see, if you check if it is k inductive for that k, then you're done. Then you don't need to check any further. Okay, so yeah, so otherwise, you bump k, you check if there is a counterexample, and see if it is k inductive for that long, and keep doing it, and therefore, yeah. So this can either terminate with a counterexample if the system is not safe for p, okay, or if it is p is true, then it can terminate sooner with than a loose completeness threshold. Okay? So this is k induction. Okay, so which has you doing two checks. Okay, one, the basic BMC check, base k, and the inductiveness check, which can be considered as a check for when to stop and conclude that your property is verified. Okay, is it clear? Any questions here?
So if we have that some property is k inductive, then that means that exists some stronger inductive invariant, right? Now, if we know that like the property P itself is satisfied in all of the initial states, how do we have a guarantee that the stronger invariant is satisfied in the initial states? Like P star is satisfied in the initial states. Because we should need that if we want to say that P star is an inductive invariant and hence P is correct.
I mean, let me understand your question. So this is not producing the inductive invariant. It's
Right, yeah,
only indirectly showing, but you care. I mean, no, this is, yes, K induction does not produce an invariant, okay?
right.
It just does a check, which if passes, then it means that there is a stronger, something which is strong, but which can be weaker than your set of reachable states, which is adequate to guarantee that your property is verified. Yeah, so I guess if I understand you correctly, was that your question?
So no, my question is in the soundness theorem, I can the fact that P star should be inductive is okay, but why should it be why should it be an invariant in the sense that why should it have the initial states inside of it?
Oh no, that you will have to check, and that's what you're kind of checking here. Okay, if you're only using that inductiveness check, eventually, yeah, you will have to check that that your initial state is included in that. Okay.
Yes, we are checking whether
Doing more than that, no. So here you're already that's what you're doing here, but I'm doing more than that, because then you won't know, so you might end up but you will have to yeah, so what if you're also finding that witness, okay, to the counterexample in case where IS naught is not contained in that inductive invariant. That's all. In that strongest.
So if P is K inductive, then we have, I mean, I'm convinced of the fact that then we'll have some P star which is stronger than P, which is inductive. But why should that P star have an initial state? Here we're showing that, okay, P does not have an initial state. Why should the stronger P star have all the initial states inside of it? That is my question. So, I mean, we proved that the whatever like P star may exist, that would be inductive. But how are we checking that whether that whatever P star exists has all the initial states inside it?
Because you are, the first step itself checks if that IS naught is inside P, correct?
Yeah, but P star
Oh.
might be smaller than P. Like the green thing might not contain I. How are we?
But you're removing only those things that lead you out of I. Okay, so I, you could have. Uh, how can this not have? Uh, if I is, your question is why should I be contained in this P star?
Yes, yes, yes.
But then if I is not contained in that P star, that means that there is some state from I that will lead you out of it, correct? So and that's what will be caught by this counter example thing, because you're simultaneously checking.
So that would be caught in some like later stage SAT base K counter example.
What?
So that won't be caught in the first SAT check. It will be caught in like the SAT check inside the while loop. Is that sort of the idea?
Yeah, but I'm doing that. You see, if it is one inductive, the first check will say that okay, IS naught is inside P naught, inside P, and then immediately I will check if it is one inductive. Correct. So the check for one inductiveness immediately proceeds. Okay, from see IS naught is contained in P. Okay. So if it is not, then zeroth step itself will, so that means that I has a state which in zero step, I mean, there is a state which violates P itself. Okay, then you're done there. If not, then you know that IS naught is inside P. Then immediately you check for one inductiveness. Correct?
Right.
Then you first check if there is two length counter example. Okay.
Yeah, and if there is something that is not inside P but not in P star, then that will be caught here.
Yeah, but if there are no, so this check, the red check, is the first time. Okay, that's why it's important that you check that does not exist two length counter example before you do the inductiveness check for that K. Okay. So here you know that there are no counterexample of length 2. So then if it is that would have been removed anyway. Okay, you would have removed that state in I from I, which took it outside of I in one step. Okay, that would have then, when you do the two inductiveness check, it's only checking for that. Okay.
Yeah. Okay.
So then that's
the
why
second,
you get that. Yeah.
Yeah. So it's the second red check which is giving us the guarantee that all the things in, like if there's something in I that is not in P star, then that will be caught over there.
Correct. Yes.
Right. But in general, P star may not have I.
No. The general P star may, no, but P star, yeah, okay. So I guess there is this, what is misleading is I've shown as though, yes, you're right, man. So I've shown as though this is a special case, which I is inside P star. So there can be some states here, okay, which can get you out, okay? but that would have been, but every state in I has to satisfy P, okay? So it has to be inside P, but it may have, no, this is still correct, okay? Yeah, but yeah, there might be some states here that may be in here, okay? Which will be removed, okay? Which I think that is what is misleading, okay? That I may not be completely inside P star, okay? All of I may not be completely inside a P star, okay? Inside P star, okay?
The first check guarantees that it will be inside P.
Correct. First check is that it is inside P. And no. No. But why? Uh, but this is no. But this is the largest state. No, I take it back. See, P star is the largest state that does not have any. No, you're wrong. Okay, I take back what I said. It is the largest fixed point that does not have any state that gets you out of K. Okay, that's why I has to be inside that. It's the largest, the weakest thing that does not have any state, a P state, which take you out. Okay, so in that sense, it is still, yeah. So because if there is some I that from I there is a state that gets you out of P, then it's wrong. So it has to be inside I, and because this is the largest, uh, the weakest predicate. Okay, so that is the guarantee. Okay, so it is the weakest P star among all inductive invariants, the weakest P star that that removes all the K. Okay, all the P states that get you out of the thing. Therefore, then I should be there in that.
So if P is correct, then I should be inside P star. But if it is not correct, then it might not be completely inside P star, and in that case, that like second red check will catch that.
Correct. Yeah. Yeah, that would have that then would have caught. Okay, so it's, yeah, you could just do this, continue to do this, and then only check if IS naught is contained in that. Okay, but then you don't have the I'm sorry, no, the counter example thing. No, you don't get the counter example, the actual path that led you to not P, you will not get. Okay, that's what. So I answered your question wrongly. Okay, in the first thing. So the P star, since it gives the weakest inductive invariant that eliminates all states that get you out of P in one or more steps. Okay, that's why P has to the initial state has to be in that. If not, then you are, then P is not true for that system. Yeah.
And in that case, then this second red check will give us that particular initial state which leads us outside of P.
Yeah, and it is also giving the actual counter example, huh?
Yeah.
Because giving you that entire path.
Yeah.
From the initial state. Yeah. Yes. So yeah, questions? So let me, okay. So one point that I want to make, any questions? So yeah, so you will have to, yeah, there are two ways of doing this. One is here, and I'm combining it by these longer and longer counterexample paths only to get the exact counterexample to that state from the initial state, violating state. Otherwise, you can do the just the check if the initial state is contained, and then you're done. Yeah. Yes. Yeah. So, I mean, checking about completeness. Okay. So the way that this thing is stated is really not complete. Okay. And there is an additional, so this inductiveness check is the way it is stated. If it holds good, then it's okay. But it is not complete in the following sense. It may not terminate. Okay. If it terminates, it gives you the correct result. That is soundness. Okay. And that is guaranteed by soundness, that if there exists a K, then there is if a K, it's K inductive, then there is a K inductive invariant. Okay. I'm sorry, K inductive. Yeah, if it's K inductive, yeah, that, and if the initial state is contained in that, then you have a guarantee. The completeness question is, does it always find for some K, if the property is safe for the transition system, that it is an invariant for every state that is reachable from the initial state, then is it always guaranteed that there will be a K, at which point it will be inductive. Okay? That one requires a little bit more strengthening. You have to have a stronger check. And I'll tell you why. This algorithm may not terminate. It is sound, in the sense if it terminates, the check that you get is correct. But if for some safe properties, this may not terminate. Okay? And here is that example. Suppose to the transition system that I showed you before, I added this piece here. States 6 and 7. Now here, what will happen? See, this is a Q state, which not only gets you out of a non-Q state, but also to one in which it is Q. So therefore, this formula, that is the K inductiveness checking formula, is always unsat for all K greater than or equal to 0. Why? Can someone tell me why the K inductiveness check fails forever? Why? This is the exact check that I'm doing currently. You see, because
So there might be some 66667 paths.
yeah, see, because there's a self loop here. Okay, there's a loop involving the K. Therefore, I can construct longer and longer paths that where Q is repeated, where the state 6 is repeated, and from which there is always a state, a successor state going to a not Q state. Therefore, this can never be valid for any K. Okay. Therefore, what you need, so this is the only case in which it does not terminate. So you will have to, it's enough, you will have to, you need to strengthen the hypothesis with a check that there are no repeated states in the hypothesis part. So this antecedent that you have in here is only saying, oh, there is any path, okay? But these kinds of situations where you can construct longer and longer with repetitions, you can keep on extending that path with the same state from which there is always continuously something which takes you out of a Q state. So strictly speaking, you have to strengthen the antecedent with this condition. And that is a bit expensive, okay, because it has a quadratic, okay. So for a pairwise, every state on this path has to be distinct, okay. It has to be a non-reoccurring, no, that path in here should not have any repeated states, is what you need to additionally check. Okay, with that check, then you.
So I did not get how that formula is unset.
Yeah, say, so for example, path of length 1, okay? So Q is a Q state, following state 6, okay? That
I
gets you.
will take a initial state to be 1, then it is satisfiable, right?
No. But here, see, what is the inductiveness check is doing? It is not looking at only those states starting from initial states, okay? So it is saying, so let me include all the Q states, yeah? Let me include all the states that
Saying it's not valid, right? Not unset.
Yeah, this is not unsat, but what I'm saying is, no. It is unsat for every K. Oh, it is not unsat, okay? There is always a state, okay, in which, okay, this one is, oh,
It's not
I'm sorry. No, this should be valid, okay? I'm sorry. What I have as unsat is wrong, okay? This one, this implication should be valid. What I should have had is this implication and not of Q is unsat. Okay, good. Now I think that is where the confusion was. So I should have said this is
not unset.
Yeah, this is never valid. Okay. No, this is correct. So if this is,
It is correct actually.
It's actually
because
correct.
you can take
Correct.
K loops, and for the K plus 1th iteration, you can go to 7.
Yeah. So this is, I'm sorry, I take it back. I got confused myself. This is correct. And the reason that this is never unsat is, I mean, is never unsat is because.
I think that it is, there exists a assignment which makes it unset, which makes it false.
Correct. Yeah.
Okay.
Yeah, that's because I can construct longer and longer Q that takes you to something which is not of Q. Correct? Yeah. Yeah, this is the validity check. Yeah. So you will have to eliminate those, you have to check only for repeated, that you have to ensure that there are no repeated things in there, okay? So that, what am I saying? Yeah, this is the completeness for safety statement. If P is an invariant for M, then there exists a K, some K, finite K, for which P is K inductive. And that thing itself is, yeah, maybe it's getting late now here, so I will show you. Maybe I'll do this next time when you have had some time to digest the algorithm. So I have kind of a justification for the soundness as well as completeness. Okay, but nonetheless, let me stop here. Okay, because going through my argument for the proof might be a little bit may not go well towards the end of this thing. So I will revisit this, and if you have time, I mean, once you've had time to digest this thing, maybe you have more questions. I'll upload it and you look at it, and then we can go through the proof next time. So, but the thing that I want to emphasize is, as you can see, what is the key thing in here, in this method. So here I'm assuming that you will add this, okay? You see, sometimes, adding this will increase the size of the formula, okay? So what some implementations of K-induction leave this thing out, okay? It is okay to leave this thing since it is still sound. The method is still sound. It does not give you a false answer, but there might be some properties for which it may not terminate, okay? So sometimes it is left out because anyway, if this, but you can add that check. But the important thing is that this is a method, does not require two key takeaways. One is no existential elimination. But of course, even this you have to check longer and longer K formulas. But the hope is that for safe properties, you may get a convergence faster than the way that you do with thresholds, because usually reoccurrence thresholds are too approximate, too loose.
What does exactly this algorithm do?
What it does is, you can say that it is a complete bounded model checking method. Okay, so the bounded model checking method had only the red part. Okay, and you had to keep running it, this one, till you reached. Okay, so this true, you had to run it all the way up to the completeness threshold, the number of iterations. Whereas here, you're doing this inductiveness check, and then you are able to terminate it, okay, and then get a conclusive proof that it is doing. It is a complete bounded model checking method for safety properties. Okay, so given a safety property and a transition system, it says yes or no without needing a specific completeness threshold. Okay, that's what this method does. Because this is a termination check if it is verified. Okay, if before you reach that, if you find a counterexample, then it is unsafe. Okay, but saying that it gives an affirmative answer to say that it is safe without needing a completeness threshold number. Okay, that's what this thing does. Is it clear? Does it answer your question?
Yes.
Okay. Okay, are there any other questions? If they're not, I will upload it. Please go through it. The next one that I'll be talking about is what I'm hoping that you will implement. It still has this has the disadvantage that the K sometimes can be very long, and you see this one does increasingly bigger and bigger formula. So there is another method which does this by using repeated calls to SAT. So every SAT call here is one longer than the previous. In each iteration, the SAT check that you will have to do is on a formula which is one longer. Therefore, if the K, even this K for convergence for safe properties may be small, okay? But if it is not safe, yeah, if it is, if the counter example, yeah, if it is safe and then that, maybe the lack of counter example to induction can be, all counter example to induction from P can be eliminated with a small k. This is comes out winner. Otherwise, you will have to do a bigger and bigger k. So there is another version in which each SAT call that you will have to do will be always on one step. Okay, one step T, and that seems to, I mean, that is the best bounded model checking method that exists to this day. Okay, and that was invented about 15 years ago. Okay, maybe 10 years ago, 12 years ago, and it is very, very, probably the best method that has been used for all, especially for hardware model checking. Okay. And so I will end here. So I will upload this. Please go through this, go through it, and if you have any questions, any doubts, you come back again, and we will discuss, and I will show you the proof, and then move on. And the next class, I will also cover the counter example for CTL model checking. Okay, if you have any doubts about that, yeah. I mean, I will cover some basics of it that you to answer your questions, and so you will still. I would like for you to implement it in your as part of your assignment. So by next class, I would also like you to pick up your teammates, okay, and then give that information to me. Yeah. Okay. Any questions? Any further questions? If not, I'll stop here. Zubin, if you're still there, are you still there? Zubin left. Okay, so fine. So I'll stop share. Yeah. So